Okay, we're being asked to find the derivative of x squared, and we're going to use the definition of the derivative to do that. So what is the definition of the derivative? Well, it's just the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Okay, so how are we going to use that in this case? Well, we have a function. The function is x squared. And so all we have to do is plug in x plus h into the function and plug in x into the function. So just to be really kind of clear about that, we're taking this x plus h and we're plugging it in. And for that matter, we're taking this x and plugging it in, but it's already an x, so nothing really changes there. Okay, so let's go ahead and do that. So this is the limit as h approaches 0 of x plus h squared, so we plug that in for x, minus x squared, all divided by h. Okay, so now we can just go ahead and start simplifying this limit and see if we can solve it. So let's expand out x plus h squared, and we'll get x squared plus 2xh plus h squared. And then we still have this minus x squared over here, divided by h. And now look at this x squared, that's a positive x squared, and a minus x squared, those will cancel. So that's nice. That's simplified a little bit. And so let's see what else we have. So we have 2xh plus h squared, all divided by h. That's what's left over. Sorry if that's a little bit close to the last step. And it's making it hard to read. Well, that's making it even messier. Anyways, okay, let's factor out an h out of the numerator. So both terms have an h, so we can pull that out. So this is 2x plus h, all times by h. You could verify that that's right, just multiply the h back in. You would get 2xh plus h squared. Okay, over h. And now these h's can divide out, and we're just left with the limit as h approaches 0 of 2x plus h. And now we can take this 0, plug it in for h, and we're pretty much done. So this is going to be 2x plus 0, but of course plus 0 doesn't contribute anything, so the final answer is 2x. So the derivative of x squared is 2x. Now a little notation. We have the original function f of x is equal to x squared. If we want to denote its derivative, we write a little prime symbol. So f prime, meaning the derivative of f, is equal to 2x. That's what we just figured out. So this is the first time we're seeing the derivative as a function. And this process we went through just now, solving that limit, is really only maybe a quarter of the whole picture. Meaning this is just some algebra, we figured out the right answer, but we really need to understand what's going on, and that's what we're going to do now. So let me show you a picture of what's happening. So here in red is x squared, the original function, and in green is its derivative, 2x. The derivative will tell you the slope of the tangent line to any point on the original function. So for instance, let's say we want to know the slope of the tangent line when x is 3. So x is 3. There's the tangent line to the original function. So this is the tangent line to x squared. Let's say we want to know the slope of that tangent line. Well, all we have to do is come up to the derivative right here, and find out what the value of the derivative is. So that value is 6. So that 6 means the slope of the tangent line, let me get a thinner brush here. The slope of tangent is 6 when x is 3. I'll just write x equals 3. So when x is 3, the slope of the tangent line to the original function is 6. And again, we figure that out by just finding the value of the derivative when x is 3. The value of the derivative was 6. And if this seems a little mysterious to you, we can even verify that by just kind of eyeballing rise over run. So you remember how to find the slope of a line if we have this graph that's all marked off for us. So we can check. We went from 3 to 4, so we moved over by 1. And how much did we move up? Well, we started at 9, and it looks like, let's see. Looks like we're ending at 15, so that's 1, 2, 3, 4, 5, 6. We've moved up by 6. In fact, you didn't have to count that. 15 minus 9 is 6. So that means we have a change in y. The change in y is 6. The change in x is 1. That's how you find out. That's what slope is, change in y over change in x. So the slope of that tangent line really is 6. Okay, so I hope this didn't get too messy for you. I was just trying to help you see, verify that the slope of that tangent line really is 6, and the derivative is what initially told us that. The value of the derivative told us the slope of that tangent line. Let's do another example. So let me erase all of this. Let's do when x is -2. Well, just looking at the slope of the, just looking at this tangent line here, we know its slope is negative, so we're expecting, that's kind of a poor drawing, so we're expecting the derivative to be negative, and of course the derivative is negative. So that's good right off the bat. So we want to know the slope of this tangent line. Well, we just come down to the derivative. It tells us the slope is -4. When x is 2, the derivative is -4, which means the slope of this tangent line is -4. So I hope that this is making some sense to you. This is understanding the relationship between a function and its derivative is a really important step in understanding, really absorbing and understanding calculus. Let's do one more example. Here's 4, when x is 4. So we can come up to the function, draw in the tangent line, and now we want to know the slope of that tangent line. Well, all we have to do is check the derivative. The derivative looks like it's 8, and so the slope of the tangent line is 8. Okay, I hope this helps. I'll see you in the next video. We'll do a couple more examples.